Hi, I'm John Foro, and we are doing a live class right now by special invite only for 5 different instructors across the country. We are going to record it, and if it seems like it was a well-received class, I'm going to put this out on social media, LinkedIn, Facebook, all those kind of places. So at the end of the class, I'll field questions from the 5 by special invite instructors. And the subject matter of today's class is going to be everything there is to know, that I know at least, about high voltage batteries. That's a very hot topic within the automotive industry right now. We know that we're switching over, at least a large percentage of the automobiles are going to be switched over to electric drive type. And battery technology is kind of the mysterious thing regarding being able to get the most amount of life out of these batteries, being able to service these batteries, being able to, go ahead and provide different services for your customers' cars that come into your shop. So real quick, looking at the slides, I'll go over some of the content that we're going to talk about here. The introduction we've already taken care of. We're going to talk first, in case you're not at the instructor level, the people that are joining us live here today, we're going to talk about how a battery works. We're going to talk about the different stages of battery technology, how we evolved to what we're currently using in most abundance, which is lithium style batteries. And we're also going to talk about what the future holds for us as well. We're going to cover the battery management system, the BMS. We're going to cover that in kind of detailed aspects of stuff. We're also going to talk about building a battery wall, and primarily some of the stuff that I've got covered here today, I know a lot of you other instructors that are teaching at secondary, post-secondary, or maybe even professional techs like we do across the country right now, maybe want to use some of these philosophies. So there's a lot of different little tasks that you could have your attendees of your classes actually do to help them fully understand the whole battery technology stuff. We're going to do, it says live vehicle testing, it's actually going to be doing live testing here in the actual class here on primarily different types of components. And then we're going to kind of end with some EV chargers, because technically they have to charge up a high voltage battery. So real quick, as we go through this stuff here, we know that the battery, the high voltage battery, is oftentimes the most expensive part of an electric drive vehicle. So the consumers have a lot of concerns. They don't want to have to buy, a $3,000 battery up to, in some cases, a $20,000 battery, plus add labor on top of that. And we don't want to just take these batteries and, because the battery has failed, go ahead and scrap the whole vehicle. So there's a lot of stuff that we can do as technicians to provide a service for our customers to get the longest period of life out of the battery. And that's kind of what we want to focus on throughout the actual course here today. So real quick, we're going to start with Battery Basics 101. How does a battery work? So we're going to go into this deeper and deeper as we go through the different demos here. But we have just 2 little coins, a nickel and a penny. And if I take that nickel and a penny and I just touch them next to each other, so this would be like the anode and cathode plates of a battery pack. If I touch them next to each other, and if I were to take a voltmeter, it's kind of hard to do with one hand, but I'm going to attempt it, and just touch the leads to the nickel and the penny, I get 0 volts. Now if I go ahead and separate the nickel and a penny, and I got a little piece of paper towel here, and I got to put something that's like electrolyte on this. So the easiest thing to do is to put some saliva. There's a lot of acidic content in that. So I'm going to put some saliva on here. And depending on how much acidic content is in the saliva of the person doing this, that voltage reading is going to differ at this point. So now I have approximately, it's kind of hard to look at upside down, but approximately, say, 30 millivolts or so of electricity. And no matter what the battery technology happens to be, that is the simple concept. I don't care if it's a lead acid battery, an AGM battery, all the way up to lithium or sodium style batteries. That's the basic principle of how this works. So that's a very fun, safe activity to get started. You can use it in a basic electricity course. You could use it in a course like this about high voltage batteries. Now here I have a regular battery that's been cut apart. This is a bad battery, so that's why I sacrificed it for this. And we can kind of see the construction here. So we're going to talk about what all is inside of a battery pack. So I've got the anode and cathode. That's a positive and negative leads, basically. But here you can see I actually have 6 individual cells. Now those 6 individual cells, because this is a 12-volt battery, those 6 individual cells, if I were to break these apart, I would have what we call plates, and then I would also have separators. So the separators inside here are actually represented in black. Now this was a lead acid style battery at one time, so the white foam, which we'll talk about in a little bit here, that's kind of distorted, so it might be a little bit difficult for you to see the black lines going between those. Now those separators, I'll have many individual plates inside each one of these individual cells, and then those plates are separated by the black separator. Now just for sake of, not getting too far ahead of ourselves, those white pieces of like cotton foam type stuff, those are like sponges so that the electrolyte inside this battery could actually have better contact with the actual plates. So there was a time going way back when we didn't really have that real concern, and we had the serviceable batteries, and a lot of times going back to like the 70s and 60s and stuff, we took the vent caps off, we could add electrolyte to the top of the battery, we could actually go ahead and put some water in the top of it, distilled water if that's the case. Couldn't have too much of it, because here's something that happened, and this becomes important with today's technology as well. If I had too much water inside a battery like this, let's say it was a serviceable battery and it was low and I just put too much water in there, well, water would freeze if the temperature got too cold. So this is just going right back to basic chemistry here. When water freezes, it expands, and the separators, which are just, in most cases, little pieces of plastic, would actually crack. And now, depending on how bad it froze, I could take some plates and have them short out inside. So this still applies. We still have separators in high voltage batteries and stuff. We can't allow that dead short, because that's gonna not only make the battery bad, but in the case of like a lithium battery, that's one of the stages of thermal runoff here. So we need to go ahead and keep that in the back of our minds at all times. So some of the reasons why any battery, doesn't matter if it's an old school battery or a new school battery, one of the main reasons why batteries fail over time is because the internal impedance or resistance of the battery starts to get higher with the longer life usage out of it. So now we're just going back to simple Ohm's law here. What does that do to amperage? If the resistance inside this cell changes, what does that do to amperage, right? It's a teeter-totter. They can't both be high at the same time. What does that do for the voltage capacity of this? So we're going to cover all that in greater detail as we go through the class here, but that's one of the things that happens. And if the impedance of those cells start to differ too greatly, we have what's called an out-of-balance battery pack. So in a lot of the examples we're going to show you today, we may have, 15, 20 individual cells, but on an EV, we will have far greater amounts of individual cells, no matter what they look like. They could look like, this is a nickel metal hydrate style. They could look like this, which is kind of like a cartridge style, or like in the cases of some of the some of the Tesla models that are out there, they actually use these, which are 18650 lithium battery cells. And there's over 1,000 of them. So this is all kind of new for some people, I'm sure, but other people, you know, I'm not telling you anything new or exciting at this point. So I have a lot of different ideas planned for us here today. And what I'm going to talk about is what in the automotive industry is basically important for us to know, because the ultimate choice is not always to replace the high voltage battery. The ultimate choice would be to prolong the life of that high voltage battery. So I've got a lot of different tools we're going to be using today, a lot of different demos. As the day goes on, we'll continue to talk about different aspects of stuff. But in my real electric vehicle training class, one of the tasks I have the attendees do is build a little 12-volt battery kind of like this. Now this one is not 100% built, this is just in the stages. But I have a battery management system here, and I also have the individual cells. So there's a total of 21 lithium 18650 battery cells here. And I don't have the whole thing spot welded together and everything yet, because I have another one that's fully assembled here. We're going to be using some of these cells for different parts of what we're going to be doing today. So I just kind of wanted to show you the composite makeup of it. So just for sake of camera usage here, what it would look like when it's all done and fits inside the battery case is this. We've got the nickel strips spot welded onto the top of it. And those nickel strips spot welded onto the top of it is what's actually taking, in essence, about 3.5 volts from each one of those lithium cells and putting them so that it creates the 12 volts that we were talking about. All right, so with that being said, let's talk about another concept that's out there. One of the concepts is, if it's an old-fashioned car battery, we felt pretty confident as technicians on how we would go about testing it, right? So we, check the open circuit voltage, and then eventually at some point we'd do a load test. So there's two different popular style load testers that we had to choose from. One of them is a capacitance style load tester. We'll come back to that. And one of them was a carbon pile load tester. So a carbon pile load tester, basically you take the two leads off your battery tester, hook them up to the positive and negative leads of the battery you're testing. Lots of times you'd have a separate amp clamp just so you get an amp reading. We'd read the sticker on the battery and we would deliver half a cold cranking amp load to it. In essence, as I turned that knob, I was just creating a controlled short across the positive and negative. That was a great way of testing batteries. However, with today's electronics, all the industry has gone to capacitance style. So capacitance style, so here we have an Autel capacitance style battery load tester. And what this does is this would have the leads coming out of the bottom of it, and those leads would actually still hook to the positive and negative. It would not need an amp clamp for this test. And the way this works is it works very similar to our leads on a milliohm meter. So you'll notice, here's the positive lead. These are called Kelvin leads because I'm assuming the guy that made these has probably got the last name of Kelvin. But you'll notice that I don't have just one wire coming to the end of that lead. I have two. So why do we have two? Well, one of them is going to be a traditional that's going to be able to read the volts, right? The other one, however, is actually creating, it's different from one tool to the next, but is actually usually sending about an amp of current down. And then it's measuring the voltage drop that occurs. So that's how the capacitance style battery load testers work. And then it's using a much smaller load test on the battery pack, but it's in some ways better for electronics, and it's definitely safer than the old-fashioned carbon pile load test. But let's talk a little bit about load testing real quick. So let's say I wanted to go ahead and do a load test on an electric vehicle's battery pack. Now, I don't want to break it down and have to do, in some cases, 1,600 individual cells, right? That's going to take a long period of time. As of right now, there is no tool out in the automotive industry, at least to my knowledge, that can load test the entire high voltage battery all at once. It tells me a lot of information. There's a lot of tools we're going to be covering here today. But there's not one that can actually go in and do the complete loaded test on a battery. However, this is a little tool that I put together that if I wanted to do technically a carbon pile load test on an individual cell, it's very simple to do. I can I'll just grab this particular cell right here, hook up to it, and then I'll take a meter. Let's take this guy because he's got points on him. I'm going to put it on voltage, kind of make it so it stands here. And I'm going to put them inside the positive and negative leads. And this style nickel metal hydride battery pack, fully charged, should be about 7.5 volts. So we can see we're not exactly fully charged here. But as I push that button, I am basically going to create a load going across it. So as I create the load going across it, we're dropping well below a volt. So the outcome of this test for this particular cell is going to tell me that, you know, it's going to have to get charged and redone first, but I know for a fact that this battery cell is bad. So with that being said, before we get real far ahead of ourselves, we showed you an older style battery pack. Here is a nickel metal hydride style battery pack, and you can still see that it still has the individual cells in it. And you can also still see that we have the individual plates, we have a separator. The separators are like pinkish in color on here. And it's still, the technology part of it is still all pretty much the same as we had before with the older style battery pack. Now the 18650s, they're designed a little bit different. We'll talk in greater detail about that here in a second. But the nice thing about the Autel, you know, battery tester here, so this will do everything that you want for low voltage batteries like you always wanted to do, but this actually has a lithium battery test built right into the menu that will do a 12 volt lithium battery. So some vehicles that use start-stop technologies have those. And it will also test up to a 48 volt lithium battery. Now, in order to do that, that's going to require us to have communication with the battery management system, because with the higher voltage, we need to protect that battery. So this is very nice. So for mild hybrid applications that use that, I can still test that and do an overall loaded test on that low voltage lithium battery. As technology changed with batteries, here is an individual plate out of a battery. So you can see that over time, you know, the electrolyte's done its job on this. So this is the actual plate. Now, they actually encompassed it in this absorbent baggie type, because remember, old-fashioned batteries, this would just be inside there, there'd be the separator, and then we would just rely on the liquid electrolyte to try to penetrate this as much as possible, so it would actually want to create voltage. Well, as technology started to evolve, they determined that, hey, if I go ahead and encompass this plate, so these are very fragile, so that's why I'm going kind of slow there, inside of an absorbent bag, well, even if the electrolyte level was low in the battery case, it acts as a sponge, so that entire surface area of that plate is still going to be encompassed by the electrolyte, whatever type of electrolyte they were using at the time. So that's how we evolved from regular standard lead acid serviceable type of batteries into, you know, something that kept building as building blocks to get better performance, if you want to call it, and more longevity out of a battery pack. So that's how we slowly start to evolve. Now there's still some battery acid on here, so I'm just going to throw this on the ground real quick as opposed to letting it eat a hole in my tablecloth. So we got from lead acid, saw the first stages of battery technology as it started to increase here. Now let's talk about that impedance, right? How can I test a cell's impedance? Well, I just got 4 of these right now. Technically, we probably only really need to use 2 of them, just so you see an idea. Now, let's just play the land of make-believe here shortly and talk. Let's say that an electric vehicle had 100, which they're going to have more than that. But we'll just use 100 as the number. So it's got a positive and negative side of the battery pack. I can use a milliohm meter, actually the bottom one. I can use a milliohm meter to actually go ahead and do a capacitance style test, just like I did before when we were explaining the different types of leads and how that battery load tester works. Now, as of right now, there's no tool manufacturer that's creating a tool. A lot of them are on the horizons. We'll come back to this in a little bit. But there's no tool manufacturer to let me do all the cells at the same time. Doesn't mean I'm out of luck, because remember, the impedance of the battery affects the overall balance of the high voltage battery pack. So if I can see what the balance of the cells are, so if I can see the voltages of this, I have a pretty good idea whether or not that battery pack's balanced or not. However, I have another little tool here that I'm just going to go ahead and set one of these up and turn it on. I'm going to make sure it's coming on. I've got about 48.6 milliohms of impedance in this one used cell. So with the 48.6 milliohms of impedance, this one cell, I know that's the internal resistance. It also will give me the voltage reading of that cell at the same time. Now I'm going to take that cell out and I'm going to put another cell in. And I'm going to do the same test again. And this particular one has 38.7-ish milliohms of impedance. So I'm not going to go through and waste everybody's time and do a whole handful of these, but these are used cells. I could grab a new cell and see what the impedance of that is. But again, the internal resistance inside that battery pack will change over time. Now there's things that can affect that change. So one of them would be, what is its usage cycle? By that I mean, is it commonly fully charged and then commonly go all the way to pretty much full discharge, 5% or less, and then charged again? Because that will help prolong that resistance from actually building up inside these cells. What's the downside to having, we just had 2, and they weren't that far apart, roughly 10 milliohms or so. But imagine if I had 100. We used 100 instead of 1600, right? We used 100 as our magic number. Well, that resistance starts to build across a much greater avenue or plane of the whole high voltage battery pack. So now we have cells that become out of balance. What happens when a cell becomes out of balance? Well, think about it. If, for whatever reason, this has more resistance built into it, there's something that's called DOD, stands for depth of discharge. Now what that means in fancy terms is how much of this whole, I'm pointing up and down, it doesn't really work like that, but for explanation purposes, how much of this whole cavity of this battery can electrons actually fill in some sort, right? So we think that we're charging a battery pack to 100%, but in a nutshell, most manufacturers design these to be fully charged at about 80% of its capacity. So we're not even starting with the whole potential right from the very beginning. Now, if I happen to have, we'll use that 100 number again. If I have 100 of these with all different types of, impedances, and I've tested a lot of these in the past, making little training projects and stuff. I've had some that were over 1 ohm of resistance difference, and that really is a bad cell. So one of the things that changes that impedance is temperature, right? Temperature is evolved around maybe possibly having a car, an electric vehicle outside, and it's cold outside. Or maybe as I'm charging the car, the heat that's generated, or if it's hot outside. Temperature has a large effect on the impedance, but so does how you did that charging cycle, right? So most EV owners, and I don't blame them, I don't want to be stranded either, have what's called range anxiety. So they get a new vehicle, and let's say it's got 300 miles of range with a fully charged battery. And as they're driving this thing wherever they're going, they're not going to let it get down to, 3 miles of range, because who knows if there's going to be a charger in the next 3 miles. So usually, typically about 20% or so, they start looking for a charger. And then the type of charger, as we'll talk a little bit later on, whether it's a level 2 charger, which is a slower type of charge, but better overall for the battery, or if it's a DC fast charger, plays into this as well. So we can actually have a battery that's out of balance, but we can put it back in balance and prolong the life of that battery pack. And that's what we're trying to do with being able to do diagnostics and understand how the battery pack works, understand battery technology, answer a lot of problems that EV is facing right now concerning high voltage battery packs. We're going to try to address every one of those challenges. So we have the impedance that we can test there. Now, I know that there's some manufacturers that are going to be releasing shortly a battery tester that will be able to test the impedance of the actual batteries. And what we do is we do what's called balancing the battery pack. So it's going to be a balancer, discharger, tester. Because in order to try to reduce that internal resistance, now if the battery is bad, it's bad. But if it's just got a higher level of resistance because of being out of balance, in order to try to get all the battery cells back in line with one another and balance with one another, we need to go ahead and discharge and balance those battery packs. So the tool that I have here today is just this little tool, which is not made to hook up to a high voltage battery pack. But it will allow us to go through an automatic setup, and I can go up to, I'm pretty sure the spec on this is like 30 volts or so. So I can do a 12 volt battery pack. I can do anything up below that, right? No matter how many cells are actually in it. And I can use that tool to perform a proper balance on the battery pack. Now, once I do that, I would see the difference of the impedance, and now when I go to charge a battery the next time, I'm starting with kind of not erroneous figures here of the different impedance levels. I'm starting with them all pretty close to one another again, so it's balanced. So technically, I will get a better charge out of it. Because if I did not have a balanced battery pack, so we'll just use 2 as an example here. Let's say this guy here had a whole bunch of impedance in it, and this guy over here that had virtually none. I charge these battery packs. Now, these particular battery packs are going to be about 4.5 volts or so. I charge these battery packs. What's going to happen? Number one, they're both going to be reading about 4.5 volts, but this guy that had all the internal resistance built up, as I start to accelerate the car, I start to use the car like I would, have electrical demands on it, this one's going to discharge sooner. So that is why that's a performance issue. That's why balance is so important, because if this one discharges sooner, how many times have you had a customer come to you and say, hey, can you check my high voltage battery? Because I think it's starting to fail. Because when the car was new and I charged it overnight or whatever they did, I had X amount of miles of range. But now with a fully charged battery, I don't have that kind of range anymore. On the dash, it tells me I have 30 miles of range as opposed to 50 miles of range as before. Well, that's because that one that has all the extra impedance discharges at a much faster rate than the one that has less impedance in it. And again, we're just using 2 as an example. Imagine if I had several hundred or over 1,000 of these in the composite makeup of an electric vehicle battery. So before I get too far ahead of myself, what I want to kind of do is I want to make sure that I'm covering, just as my little crutch here, some of the notes that I have in the PowerPoint here. So we did the basic battery demo with the nickels and coins. We talked about battery composition. There's a nice picture that actually shows the separators and stuff better than what we saw on the actual battery pack. What is battery technology? Battery technology is just changes. At this point, it's the change in the materials that are made up inside the battery. So we're not using necessarily lead acid anymore. You know, we'll jump from lead acid straight to lithium, which is a better technology. And we glossed over the ones, nickel metal hydrate and stuff. You guys are aware of the different battery technologies here. A typical EV battery, there's a lot of stuff inside. I've got a couple EV batteries that we're going to talk about here. Battery facts. We talked about the internal impedance. We talked about how temperature affects the overall performance of the battery. But why does it, right? It does it for 2 reasons. It does it because, number one, we said before, those separators, if it's too cold or too hot, that could cause a problem with an internal short, right? But it also affects, the temperature also is affecting the ionic movement of the electrons inside, going from the anode to the cathode, back and forth. The materials that the anode and cathode are made out of is battery technology. The charging types, so is it a level 2 charger, a level 1 charger, level 3 charger, all that affects it, the state of health and state of charge as well. And primarily, why is lithium such a big hot topic right now? Lithium's a big hot topic because it's a very rare substance on our planet. It's costly, and also in some cases it could be dangerous. A recent study shows us that, you know, let me get the exact figures here. Batteries have a 64% lower lifespan than when compared to an internal combustion engine, which is why we have all the EV haters out there, you know, saying that, hey, these cars, they're more expensive, and you know, the battery, what do we do with the battery when it's used up? We're going to address all that, but what do we do with the battery when it's used up? And lithium is dangerous because we have thermal runaway that could cause fires and stuff. So we're going to talk about that. Now, when we're talking about the temperature is the biggest contributor. And let's talk about the worst case scenario with temperature right now, with the stages of thermal runaway. So before we talk about that, it's important for us to know what is the optimum range that lithium batteries should be in. They should be between 60 to 100 degrees Fahrenheit, right? As long as we keep the batteries in that range, we don't have to worry about thermal runaway. Now, stage 1, so we talked about simple facts first. So electrolyte, no matter what substance it's made out of, that's a flammable gas. And it's going to involve some technology and some science here as we go through this. But stage 1 of thermal runaway happens at about 135 degrees Fahrenheit. The anode materials will begin to break down and allow metal to mix with the electrolyte. Now we're going to show you a video, and that metal that's mixing with the electrolyte becomes dangerous if a full-blown fire were to occur. So we'll show you that here in a second. Stage 2, the SEI, fancy word for solid electrolyte interface, that's a film that's on the anode, the positive lead there, is also affected, and as that starts to strip and decompose, that will increase the heat inside of a lithium battery pack. Stage 3, the lithium carbon fiber construction of the anode pretty much almost fully starts to break down at this point. It begins to interact more with the electrolyte, thus increasing the heat even more. At this stage is an important part because this will be one of the first signs of a lithium battery that's starting to fail. So we said that it's a gas, right? So as stuff heats up, that's simple physics, we take a solid, like let's say an ice cube, and it starts as a frozen matter there, and then it turns into liquid as it gets hotter, and then it turns into gas in the boiling point, right? So as that gas starts to expand inside of a lithium battery pack, it will start to swell. Now, that's a first visual sign that we have that there's a problem. This is a big thing to actually pay attention to. Eventually, that gas is going to find its way out, right? Because it starts to expand. That's why the lithium cell is expanding, and it will usually start to vent. Now, it's a flammable gas, right? So that's not good. And remember, I could have, 15, 1600 of these in close proximity to one another. As it starts to expand and it starts to release that gas, it will make noises. So, if you got a customer who brings you their vehicle and they say, hey, when I charge the vehicle, or maybe after I'm done driving the vehicle or whatever, once a vehicle's stationary and they're out of their car, it's making some weird noises, that's a very dangerous time for that battery pack, right? So I've got 2 battery packs here, and technically, for those of you that don't know this, my camera guy, every time you see me on a webinar or anywhere else, his name is Stephen Ferraro. He's my nephew. He has his own real estate company. I'm going to give him a free plug here. I think it's called Real View Photography, so hopefully I said that right and didn't tell you competitors. But Steve is also into gadgets like I am, right? So he's got all kinds of cool little intricate stuff as well. So these are RC style battery packs. These are lithium. Here's a brand new one, right? So it's got the little stickers on it and everything. Here's a used one from something that he bought that somebody did this to it. This is a pack that is actually in the swelling stage right now. Now he knows that this is not a safe pack to have around, but I convinced him to let us use it for the sake of this class here. So it's expanding, and whoever did this actually wrapped it in tape at the same time, as if that's going to prevent thermal runaway from actually occurring. So this is not a safe battery pack to even have around. Definitely don't try to take it on a plane or nothing like that, because it's just a couple steps away from full-blown thermal runaway here. But you can see the difference how it starts to expand. Now, looking at this, we'll keep matters real simple here. Let's just say the high voltage battery only had 21 cells in it, right? So I got 21 cells like this 12 volt battery does. And let's say this guy in the middle was the one that was starting to fail and starting to have thermal runaway. And it starts to expand, and then it starts to vent and everything else. So let's go to that releasing of the electrolyte, which is flammable. Obviously, if there's any spark around, that's a bad thing. That's going to ignite, right? But at this point by itself, it still doesn't quite ignite because there's probably not an exposed arcing or something going on in here. Plus, we need oxygen for a fire to occur, right? Now, why did it start to fail in the first place? Well, we talked about it. It could be out of balance. It could be the heat set up. As the heat starts to build, going back to the simple technology here, remember the separators will start eventually. We're not to that step yet, but the separators that are keeping a short from occurring inside there will actually start to contribute to heat as well, because those will start to melt, and then we will have little shorts, which a small short is still, we know a short's going to create heat. But when it's a full-blown thermal breakdown here, now we have, pretty much dead shorts inside there. And the problem is, if this guy catches on fire, what does that do for heat for all the other ones inside this pack? Well, they all start having greater heat. We know heat is the main cause of thermal runaway. All right, so with that being said, we'll come back to that here in a second. Going back to the slide so we can talk about the other stages here. Stage 4 of thermal runaway is up to about 400 degrees Fahrenheit. The separators will start to melt. Now, we just kind of talked about that. The problem with that is when the separators start to melt, we start to have small little shorts between the individual plates of the battery pack there. And that adds even more heat. Stage 5 is typically about 300 degrees Fahrenheit. Gases will begin to vent. Noises, it's a flammable gas. We talked about all that. Stage 6, the separators have pretty much fully melted down at this point, allowing a pretty good short between positive and negative plates inside the battery pack. And then temperatures greater than 400 degrees Fahrenheit allows the cathode to decompose. When the cathode, the negative part of it, decomposes, as it's mixing with the electrolyte, the byproduct of that is oxygen. Remember, we said we needed oxygen before the flame can occur. Well, now we have everything we need for a flame. And now we have the fire, right? And again, if one catches on fire, that's a problem. Now remember, these stages are important because in the news, you hear about EVs that caught on fire for whatever reason, and then a fire department comes, they put the fire out. They spray water on it. That's important too. You'll see the why here in a second. They spray water on it, they put the fire out. But remember, from this makeup, okay, this guy in the middle caught on fire. He increased the temperature, all these other ones. So technically, even though we had the oxygen from the canode and everything, or cathode I should say, all present here, we put the fire out, but we already started the thermal runaway of all these other cells. So we have voltage, and remember, depending at what stage they're at, we could be at the stage of where there's a small short present, which increases the heat, and then eventually we have a larger short internally, and now the next one over here, as long as there's still voltage present and there's a short, the next one over here goes into thermal runaway. And now this fire starts back up again. And it's going to keep repeating basically until every single cell, the potential is there to keep repeating, until every single cell is now extinguished and has zero voltage left inside of it. That's the dangerous part. That's why you hear on the news of, hey, the fire department came, they put this fire out, and your insurance companies are telling you if this car gets towed to your shop for an insurance adjuster to look at it, put it out in the middle of a field someplace because it could reignite, in the middle of the night or whatever the case happens to be. So those are the stages of thermal runaway. Thermal runaway fires start at above 400 degrees Fahrenheit. Here we're going to show you a video. This is my official disclaimer. Now I want to just preference this with, I actually caught a lithium style individual cell on fire, and it's pretty drastic, way more drastic than what we're about to see on this YouTube video. I just did not want to have a whole bunch of people telling me, because I have no idea who's going to be watching it, that I'm doing dangerous stuff. So we'll let somebody else take the blame for it. But I'll tell you, it's a pretty drastic thing that actually happens. Do not try this at home. Obviously, it's not safe. The key points that we want to talk about throughout this video. So this video, some guy throws a cell phone battery that's lithium onto like a charcoal grill. You'll see that the first part of it, it just immediately catches on fire, but then it goes back through more of a slow motion thing. You can see that pack actually expand and swell from the temperature rising inside. You can see the various stages. You can also see little fireballs that kind of shoot out from it as it's going through. Now that is the metallic of the anode that has mixed in with that electrode. So, electrolyte, I should say. And now when a fire department comes to spray water on it, metal shards are actually being, thrown off into the general vicinity. So it's a huge safety concern. So I'm going to click this on, and I don't know the exact author of this video, but whoever it is, I'm giving you free exposure right now. I'm going to turn the sound down and hit the play button. So I'm seeing that you guys are not seeing that right now. So let me see if I could do this again. Okay, so I'm going to start this over after it's done, so that you guys can actually see what we want you to see here. Let me go over here. Sorry about this little technical difficulty, but should be coming up. Okay. So you can kind of see how that fire starts off, that cell expanded, and as it shot, you can see it's really expanding now, as it immediately caught on fire, there were some sparks, you want to call it, but that's technically the metal shards that were occurring. And that's what happens when we're actually using water to put out that lithium fire. That's the dangerous part for our first responders. Now I got some other little tips and tricks that I'm going to share with the first responders, because your common practice of making an electric vehicle safe when you have to go up to it doesn't work on all cars. Your common practice right now is to cut a battery cable, a 12-volt battery cable. It doesn't work on all vehicles. I'll tell you why here in a second. So what do we have on an electric vehicle to help prevent thermal runoff? So we have what you see on the screen right now. We have a way to help cool off that battery pack, whether it's just a blower motor itself to use air to cool it off, or we actually have some coolant lines going through it on some of the manufacturers. Now that's important because remember, temperature, we want to control it at both extremities, hot and cold. So if it's colder than 60 something degrees outside for the perfect range of a battery to work, we would want to heat that up, right? To make it so that everything is working the way it's supposed to. Because remember, temperature greatly affects the ionic flow inside of a battery pack. And also, with the latest and greatest technology, we have air conditioning that actually is used to go ahead and help control the heat of the battery pack as well. So I never met this person before in my life, but if you've never seen Professor Kelly from Weber State University's YouTube video on electric vehicles, he's got a killer one on Tesla AC systems right now for high voltage batteries. Highly recommend it. Never met him, give him a shout out. I respect him greatly from the work that I've seen him do on YouTube. So that's one way that we actually can help control the heat inside of a high voltage battery pack. Now, we also have a battery management system. Now that battery management system is basically the main module. 9 times out of 10, it's part of the high voltage battery pack. But even this little battery pack here, this is its battery management system. This little printed circuit board here. This is the main brains. This will go ahead and be able to measure the balance of the cells. It'll be able to measure the individual voltage, the overall voltage, the total amperage draw, the temperature. In this little makeshift case here, it's just going to give me an average temperature of the entire battery pack as opposed to, individual cell ones. But as we get more and more technologically advanced, we start to have more and more thermistors like we do on a high voltage battery pack from a car, and it allows us to have a more precise overall temperature reading of the battery pack. Now the downside to this is With today's technology, with the exception of Autel, when we hook a scan tool up to an EV, we see some of the information from that battery management system. We don't see all the information available. Remember, when I plug a scan tool into a vehicle's OBD2 connector, I'm using the data bus communication lines. So basically what I can see is what information is being shared with other modules on that data bus communication line. Other modules, ECM, transmission control module, doesn't matter. You can use whatever you want as an example. They don't necessarily need to know all the different PIDs, as we call them, from the battery management system. So the battery management system is sharing select PIDs. I will get a temperature reading, right? But I'm probably going to get one temperature reading that's going to tell me an overall temperature of the battery pack. Now, if there's 1,600 cells inside the battery pack and that temperature sensor is on this side of the battery pack as opposed to this side that it's sharing the information with, I may look at it and say, no, everything looks good, but these guys over here might be way too hot, way too cold, whatever the case happens to be. Where on a traditional EV battery pack, there's multiple sensors there. So that's just one example. Now, Autel's got a scan tool that will plug directly into the BMS, the high voltage battery. And I can read everything that I couldn't read. I can read the stuff I could read before going to the OBD2 connector as well, but I can read the stuff in the example we just said of like those thermistors that we couldn't see before. And we're going to show you how that's done here in a second. So let's talk about the evolution of the battery management system, how this has happened throughout the years. So when hybrid cars first came out, battery management systems were pretty basic. So generation 1, it basically can control the direction of current flow, right? Is it charging the battery pack? Is it discharging the battery pack? You know, whatever the case happens to be. Then we have generation 2, which adds a monitoring of a few cells' data voltage levels. And it will start to give us an overall amperage reading out of the pack. A little bit of temperature, not too much. Generation 3 added more cell monitoring, so I got a better shot at being able to determine the balance of the battery pack at this point. It started to allow us to have some fault diagnostics, and it gave us the overall state of charge and state of health of the battery pack. Generation 4, which is pretty much where we're at with today's technology, added all cell monitoring, battery active safety controls, example is a pressure sensor we said, and battery algorithms, and also starts to allow us the ability to use bidirectional charging, V2X. So that's V2, vehicle to whatever, right? So vehicle to house, vehicle to building, vehicle to grid. One of the big problems with electric vehicles is, hey, our grid can't handle the load, right? Well, that's not necessarily the case, and the car manufacturers realize that, because you have your own little power plant in an electric vehicle battery. So we'll talk greater about this on like the last slide or so, but basically we have the ability to, in a perfect world, we don't have to go to this far extreme and still benefit from it, but in a perfect world, we can have solar panels and a battery wall, going ahead and charging up the battery wall with the sunlight and powering my house up off of it, and also charge up my electric vehicle. And then when the sun goes down, whatever storage capacity of that battery wall still has in it can still run the household appliances, whatever. But if that battery wall drains too much, I have an electrical source in a high voltage electric vehicle battery. Also, California has actually introduced where with V2X capable vehicles, we can actually help send some of that to the grid when people pull up and use a charger. So we can actually address some of these concerns. We'll come back to those concerns a little bit later on here today. Let's talk about the battery management system in a little bit greater details. How does it work? It has inputs and outputs like everything else. So we have our cell voltages, thermistors, pressure sensors, amperage devices. These are just a few examples of what is available there. What I want to do is before we get into some more demos here with some of these tools, I'm going to take this unique high voltage battery pack. So this is out of a 2017 Kia Niro. It's a hybrid electric vehicle. And we're going to talk a little bit about its construction because it's kind of unique. And I take my hat off to Hyundai and Kia for coming up with some of this technology here. But basically what we have is, I'm just going to preference what I'm about to do here with the following statement. Nothing I'm about to do is dangerous with high voltage. So I don't have to have my high voltage gloves on for this. This is a little training prop that I built. So I'm going to take the piece of plexiglass off. I'm going to just put it over on this bench for the time being. My battery management system is bolted right to the top of the high voltage battery pack here. We'll talk about that side of the battery here in a second. I got my main fuse, just like we always have. Now technically it's not a good battery, but there is voltage here. But I'm not touching anything. I'm not going to attempt to touch anything without putting those gloves on. That could be dangerous. I'm only going to be talking right now about the low voltage circuitry that makes this unique. So one of the things that makes this unique is they have a pressure sensor. Now, not all manufacturers have this. I'm just going to unbolt it. I'm going to take it out, and I'm even going to attempt to unplug it if I can. Well, I'm going to need a screwdriver for that, so I'm not going to take it out. But basically, I have the individual battery cells grouped into 4 modules on this battery pack. What a pressure sensor does is it measures for pressure. On the back side is the switch, right? So what does this do for me? If I had a swelled module and it starts to expand, if this switch gets pressed in, it shuts down this high voltage battery pack. It'll set a code, let you know that. Now, technically, I'm not actually 100% preventing thermal runoff from continuing on here, but I'm a few stages ahead of the fire that's going to occur because we haven't introduced oxygen yet. It's just swelling at this point. So not many manufacturers use this technology, but this is a very forward-thinking technology as far as I can tell here. Now, again, if we only have 1 inside here, so it'd be nice to have 4 since there's 4 different cells, but we only have 1, but hey, we got to start somewhere, right? So if this one were to start to swell, this would actually go ahead and kill this from actually working. This is only an air-cooled battery, so we only got a blower motor over here. There's no coolant lines or anything. This side of the battery is what makes this unique. So you first responders that maybe are watching this right now, pay close attention to this. We said before, first responders' rule of thumb is they pull up to a vehicle that was in an accident or whatever the case happens to be. Maybe it's already on fire. And they go ahead to keep themselves safe. They cut either the positive or negative battery cable, the 12-volt battery cable. Well, if you've watched my other webinars about switching contactors and everything else, you know that you need 12 volts, low voltage, to close a contactor. So in theory, if the 12 volts was missing from the contactors on this one is over here, you should contain all of the high voltage inside the battery pack. But we know that there's some loopholes there. If a contactor is shorted, well, then you're not really eliminating the threat, right? But what makes this one so different is the vehicle has a high voltage battery, the main drive battery. It also has a 12 volt battery, but it's got a 12 volt integrated battery that works the high voltage componentry inside this battery pack. So cutting the regular 12 volt battery is not going to keep you safe in this example here. So knowledge is key to be able to know how the system's designed to work, and then make sure that if you're going to be working on stuff, you know, in that case for the first responders, They got to know that, hey, that's not a viable solution to making sure that the full-fledged high-voltage thread is gone. So we could spend a long time. In some of my other webinars, we went through this battery pack pretty deeply. But for what we want to accomplish here today, that's the main stuff that I wanted to show you real quick before we actually do some testing on it. Now, let's talk about tools, right? So on the slide you see on your screen right now, what kind of tools are out there and available for us to use? Well, here's what's needed. We need some way to look at the balance and the voltage and all the components and all the different sensors inside this battery pack. We need some way to view that. So Autel's done a great job with their EV Diagnostic scan tool. I can actually do that. We'll do that a little bit later on. We also have, in Florida, we had a hurricane. And that hurricane let salt water inside some of the high voltage battery enclosures. Well, salt interacted and caused fires on those vehicles. So now there's a big concern of being able to test the battery pack enclosure. Now, if it's a hybrid vehicle, probably it's not a sealed component, because a hybrid vehicle, 9 times out of 10, that battery pack is inside the passenger compartment. However, if the battery pack is outside, so in most cases underneath the vehicle, it's got to be a sealed enclosure. So there's a tool out there. There's a couple different manufacturers, but the one that I got my eye on is made by Diagnostics. It's an enclosure leak detector, which will actually test to make sure the sealing of this battery pack is good, but it will also be able to help me determine if I have a coolant leak for the vehicles that use coolant to help heat up and cool down the battery pack. We also have a battery balancer that we're going to be talking about. It's a charger-discharger balancer, and level 2 AC charger, and then a discharging unit. So let's talk about the discharging unit first real quick. This is something that I made. Now, here's the purpose for this. This is, if I have a high voltage battery, it's probably not got 0 volts in it, right? So let's say I did all my testing and I determined I needed to replace it. And if it's a lithium style battery, remember, thermal runoff's a problem. So the only way it's safe is to go ahead and eliminate that threat. So this is something that is made for up to 200 volts that I can actually discharge. I actually discharged cell number 3 of this high voltage battery pack with this, right? I can't discharge the whole pack voltage, but that's quite a bit that I can actually discharge here. So this is something that we can do, and the manufacturers that are making the charger-discharger balancers, they can do it as well. May take a little bit longer because they won't be able to handle the full amperage all at once, but that is another way to do that. That's going to be an important step moving forward, in my opinion, within the industry, that we're going to want to keep these batteries safe through transport, so we're going to need some way to eliminate the high voltage threat from the delivery people, right? We're shipping this battery off on Monday, which is 2 days from now, to Orlando to a trade show, right? That's a big bunch of paperwork and everything we had to do to actually get a shipping department to actually ship this battery. So a large part of it is because of the high voltage. So that's something, right now, I don't have anything other than the scan tool that will do the whole battery pack at the same time. But I know there's manufacturers soon to be releasing the tools that we're about to talk about that will actually do the battery packs so that it's not as time consuming. So that is one of the tools. Now, on your screen, you've got the actual close-up of the red line tool. And I got another video that I'm going to show you of this tool in use. In this video, you'll see that I don't recognize the battery pack, but I do recognize the drive motor, which is a Tesla, right? So the battery enclosure, so that's the picture, but the battery pack in the video that's being tested, that's not a Tesla battery pack to the best of my knowledge. I don't recognize it off the top of my head. So I'm going to click on the video here, and this is from iCar's Training Center. So another shout out here to iCar. And this is found right on LinkedIn. And I'm going to make it so that you can see it. And I'm going to just go ahead and make this hopefully full screen. And it's got the little timer going across here. Hit the play button. So the timer is just going around in circles. Media cannot be loaded because of a server failure. All right, not a big deal. I'll explain what you would have saw in that video, and it's on iCar's LinkedIn webpage. You'll be able to see it. But basically, what we had in there was we had the high voltage battery pack, and we saw with that tool in use, the enclosure actually swells. When it swelled, obviously that's the time that we're testing for a leak for enclosure testing. That's not for coolant testing, coolant leak testing. So like I said, I don't have that tool. It's one I got my eye on. Every time I try to find a Redline Diagnostic booth at a trade show to kind of even find out how much it costs to see if I can even afford it, because it'd be great for me to use it in my training classes, there's never one there. I mean, the Redline booth is there, but they never have one of those tools on display. All right, so I'm going to talk about balancing a battery pack, right? So I'm going to come over to our battery charger discharger balancer. I'm going to make some room on the table over here. I've got my leads. I've got two red leads. One red lead is going to be able to read amperage. One is going to be able to read voltage. And obviously, I got the negative sides to both of those. And I can go to any type of battery. So I'm just going to use this guy, right? I'll just put him right up on top. And I've got to put my two red leads on. Now this is a LiFePO battery. Right? So it's a lithium-based type of battery. Much like you'd see on alarms and battery backups and stuff like that. I'm going to turn the power on to the unit. I'm going to have to come over to the front of the table here to operate the first control. This tool, just like the ones being made for auto repair, is going to test many and going to be able to balance and charge and discharge many different types of batteries. So I already have it set up for the LiFePO. The way how this tool operates is I can change the time that it's going to give to balancing the battery packs all through the menu system by pushing, long holding this, turning the knob, and I can select the different battery types, the amperage discharge rate, the amperage charging rate, all that stuff. But I already have that already preset. Then I would just push the button, and it's going to start going through its thing. Now, I've got it set up to do this for 5 minutes. I'm not going to make everybody sit here and watch this for 5 minutes. And what I'm going to do is I'm just going to, you could walk away. Now remember, there's individual cells. So there's 21 cells inside there. So I'd be balancing all 21 of them. Going back to the screen, I actually have a chart of what that looked like. So this is over the time frame that I had it set up. The red represents current, the blue represents voltage, and we can see over time how it's going through the individual cells and actually charging them, discharging them, and then charging them again. Because remember, we want to start from square one to be able to get those batteries in balance with one another. All right, so at this point, if you are an instructor, you may be saying, God, this is kind of interesting. I think some of my kids, we're not done yet, but I think some of my kids could be benefiting from this, or some of my class attendees. Here's some class activities that we usually do in my full-blown EV class. We build a lithium battery, which you saw. We build a battery wall with the BMS. Haven't seen that yet. We test the impedance, we balance the batteries, we discharge a battery, we charge a battery, we diagnose and test the BMS PIDs, We test the isolation and bonding, which is a huge thing. We're not going to do that here today. We use the scan tool to diagnose various EV faults, check enclosures. We test the thermodynamics and also the thermal runaway activity. So let's go now to what's called onboard chargers. Onboard chargers allow us to use a level 1 or level 2 charger to charge a battery pack. The battery is DC voltage. The current coming out of the wall is AC voltage. So we have to convert that, right? It's not as simple as just using a rectifier and then sending voltage right to the battery pack, right? We have all the components inside the onboard charger that will go ahead and rectify that voltage for us, but we have to control the rate of charge. So onboard chargers basically have a couple different facts about onboard chargers. Onboard chargers also are needed for V2X, which is vehicle to whatever. 2 types of charging conditions that an onboard charger will allow to happen once you plug a charging port into the car. We have what's called constant voltage and constant current. Constant voltage is slower to charge a battery pack. Constant current is faster. Now, with constant current, we'll never achieve 100% charge on a battery pack. So what most OBCs are designed to do is to allow that charger, that level 1 or level 2 charger, to begin charging at constant current to start to ramp up the electrical potential of a discharged battery pack. And then it will finish off with constant voltage, so it slows down. Now, with any one of the Autel chargers, and other manufacturers may be the same way, I'm not sure, but I do know Autel chargers. Any one of those chargers, a commercial charger, would come with software, free of charge. So we call it the cloud software. We can actually see that graph happening as it's actually happening. We can also look back at a previous charge session, and we would see how that amperage is ramped up at first, and then at times it will go ahead and kick itself back down. The onboard charger, also, if there's a fault that's occurring throughout the act of charging the vehicle, it will turn that EVSE, is a technical word for electric vehicle service equipment, the charger, it would go ahead and prevent that from working. Now, another tool that we've covered in the past is an EVSE tester. This is something that's actually made for electricians when they're installing any type of electrical charger, right? They can actually test to make sure that it's wired correctly. But it also has a way that it can test the circuitry for the proximity and control pilot as well, which is part of the OBC of the vehicle, not necessarily of the charger by itself. So this is not a bad tool. Even if you're not an electrician, this is not a bad tool for you to have in your diagnostic arsenal when you're servicing these vehicles. So we have the single phase type of OBC, which will allow a charging speed of up to 11 kilowatts, and a 3-phase type, which will allow a charging speed up to 22 kilowatts. Now, some of you might be saying, hey, I just bought a 150 kilowatt charger because of the NEVI, free money basically. And I know my car says that it can charge at a faster rate. Well, that's because those chargers are DC fast chargers. Now, on your screen, you see the connector. So when we're talking about using a level 2 AC charger and the OBC, the onboard charger, that is primarily for using AC charging. At the bottom of that connector, you see the 2 other terminals, and those 2 other terminals are used for DC charging, and that is going to bypass and send, because it's already DC voltage, it's going to send that voltage directly to the battery pack. Then the battery management system starts monitoring stuff. So that's why with OBCs, there's really only 2 different charging speeds. So most of the level 2 chargers out there are going to max out at at the single phase type, which is up to about 11 kilowatts. But if you get the more powerful ones, so in Autel's world, that we call it the Ultra scan tool, not scan tool, charger, AC Ultra, that has capability of going up closer to the 22 kilowatt range. All right, so let's talk a little bit about EV chargers and some of the problems that we have with EV chargers that we're trying to overcome. Well, one of the big problems is, hey, which charger should I buy, right? Not only which charger should I buy, but the electrical infrastructure of it, which one's better for the overall longevity of my battery on my electric vehicle. So let's address those. So first of all, the slower the charge, the better off it's going to be. So a level 2 charger is the better one. But in all reality, if you're driving across the country, you don't want to wait. You know, in some cases for level 1 chargers, that's usually what we call the emergency charger. If it's a 55 kilowatt battery, a level 1 charger, if it's putting out about 1 kilowatt of output, that means it's going to take 55 hours to charge that vehicle, right? We don't have that kind of time. If it's a level 2 charger and it's 12 kilowatts, you do the math, we still got several hours. However, if the car is DC fast charging capable and I'm using 150 kilowatts or more, or 60 kilowatts, or whatever numbers you want to throw out there, you can see how the time is greatly reduced. However, if I use a fast charger, a steady diet of fast charging my vehicle, that, because of the heat that's generated, that affects the internal impedance inside the battery cells, which basically shortens the life of the battery. So level 2 is probably the best for overall, but in a lot of cases, level 3 for DC fast charging, that's going to be what some people want when they're traveling around the country. Now, with that being said, we've got some other concerns with the chargers as they come about. Which charger is right for me? I've said this a million times since day one. Every auto repair shop needs a level 2 charger. You need it for 2 reasons. Number 1, you're going to get vehicles coming into your shop that says, hey, I plugged my car in all night last night and I woke up this morning and I only got 2 miles of range. So that's a charging complaint. How are you going to diagnose that without a charger, right? And number 2, remember, the battery management system's primary purpose in life is to protect that battery. We'll use heat as an example. There's other ways it protects it. We'll use heat as an example. If it's too cold outside and it has coolant capability going to it, it's going to power it up and it's going to run a high voltage heat pump to actually keep that battery within that range of 60 to 100 degrees. If it's too hot, it's going to want to cool it off. So whether it's just operating a blower motor or whatever the case happens to be, it's going to want to keep that battery safe. So what that means to a repair shop is somebody's going to bring you their vehicle. If it's a collision shop, that vehicle might be in your shop for 2 or 3 days. Well, you're running voltage out of the high voltage battery that whole time while it's in your shop. The whole time while you're doing brakes on it or whatever the case happens to be, if the battery management system decides, hey, I got to protect the battery for whatever reason. So I can't give the car back to the customer with 3 miles of range and say, hey, good luck getting to the next charging station, right? Can't do that. So I'm going to have to, give them enough charge to get to their next destination. Now, with that being said, which charger is right for me? If you want, you don't necessarily need a commercial one for those applications that we just said. If you want to collect revenue from allowing people to use your charger and then collect, $10, $20, whatever your rates are going to be for them to charge up their vehicle, then you need a commercial charger. Now those commercial chargers come in all different shapes and sizes, all different power outputs, including level 2 and level 3 or DC fast charging. So that's a scenario that you can decide, right? Also, all of the Autel chargers that are commercial do have a screen on them, so you can actually incorporate the usage of that screen for advertising purposes. So you could run your own ads on it, you can pay people, or you can charge people to run their ads on it. So it's another revenue choice. But that is totally up to you. You also have the ability, when you're installing a charger in a parking lot, you got to use a little bit of sense if you're going to put it outside for people to use. You want to not make it so that only one car has access to getting to that parking spot, right? So put it between, if it's only got one charging gun or one charging cord coming out of it, put it between two parking spots, right? Because this way, if the car in the first parking spot is gasoline, right, at least the car in the second parking spot could actually be electric and be utilizing it. So you could be generating income. You also want to pay close attention when you're setting up the strategic placement of your chargers. Remember, it costs money to run electrical infrastructure out to the chargers. So you want to try to keep this as close to the incoming electrical source as you can to save you some of that electrical infrastructure costs, right? So if it's a home application, let's say, and my electrical box is on, you know, the right rear corner of a 2,500 square foot garage, I wouldn't want to put it in the left front corner of that, because I've got to run the wiring and everything all the way over to it. It's going to cost me more money. I'm going to put it as close to my electrical service box as possible. All right. We also have another big concern right now. And that big concern is there's a state, I'm just going to say the state, right? So I know for a fact that New York is going to all electric buses, right? The problem with that is we need to have chargers. And in that case, for a bus, that's a really big battery, we're going to want to have DC chargers. The problem is depending on the size of those DC chargers, the electrical capabilities coming into your house, into that facility to actually run a DC charger may be pretty out of date and antiquated. So the choices would be to change that whole electrical infrastructure, or what a lot of places are doing is they are creating what's called a battery wall, or a battery block, as some people say. So what I have here in front of me is a battery wall. This is a 48 volt battery wall that technically, when it's fully charged, is about 60 volts or so. So I'll show you the voltage of that battery wall here real quick, because I'm not even really sure what the actual charge of this battery wall happens to be. So we're going to find out here together. Positive and negative leads. We're about 54.3 volts. So imagine if we did it like this. I have a battery wall that's obviously way bigger than what we're doing here right now. I have a battery wall, and that battery wall feeds the electric vehicle charger. And then the battery wall itself is plugged into the existing electrical infrastructure, right? Now these battery walls are also going to be used in those smart homes that we referenced earlier, and then we'll talk more about here in a couple more slides. But what that does for us is that takes the strain off of the existing infrastructure. So what I have here is I have an inverter. This is DC voltage. The battery wall is DC voltage, but I'm going to run an AC charger. We're going to keep this safe because there's not a whole lot of room on the table here. So we're just going to charge, we'll charge this guy. This has been our test guinea pig, so we're just going to do this guy. So here's a 12 volt battery, which is good because that's a 12 volt charger. Here's my two main leads coming off the back of this inverter. I'm going to go ahead and I'm going to power up the inverter off the battery wall. Now you might see a little bit of spark when I first hooked this one lead up. Not a big deal. Okay. Now, with that said, I come around to the front of my inverter over here. Right now it's turned off. I'm going to get this kind of set up and ready to go here. I'm going to take the red lead from my charger. I'm going to hook it up to the positive, the black lead to the negative. I'm going to get my little amp clamp set up here. And I'm going to take the the power cord from my 12-volt charger, plug it into one of these outlets on the inverter. I'm going to power up my inverter. So it's a 48-volt inverter. I'm getting that power from my battery wall. Charger's not been told to turn on yet, which is fine with me. I'm going to go ahead and set up my little amp clamp and get an amp reading here. I'm also going to hit the min-max record button so that we can catch this on camera a little bit better. And I'm going to hit the charging button. And as it kicks on, I've got a reading of about 9.6. So I've got 9.6 amps coming out of that. So I'm going to hold this by the camera. Not sure which camera is on right now. So I'm going to hold this by the camera and hopefully you can zero in on that, about 9.6 amps or so. See if it clears itself out. There we go. All right. So with that being said, now I'm going to do the same test. But this time, I'm not going to use the inverter. I'm just going to take this and plug it directly into the 110 outlet. And if it goes according to plan here, we should see a higher amperage reading coming off of this. So I'm going to have to get this guy out of here. Let's just turn my inverter off. I'll go ahead and remove these leads for the time being, just to get them out of the way. Find the electrical cord. Plug this guy in here. Come back over to the front of the table. Hook this guy back up. Go ahead and get my reading back here. Clamp this around, hit the min-max record, hit the start button, let the charger actually turn on. And I've got an initial amperage draw of 12.95. All right, so with 12.95 as opposed to 9 amps, 9.6 amps, right? So it's not real important because this video is going kind of long here. So we can see that the amperage draw is considerably less by using a battery wall with the inverter. Now the battery walls that are going to be placed at commercial locations are going to have their own inverters built into them and all that stuff, so we don't have to worry about that. But I don't have the same type of load on the electrical infrastructure as I do with plugging directly in to, in this particular example, a 110 extension cord here. So I'm going to make this so it stops beeping and just unplug this. Now, with that being said, let's go back to our PowerPoint here. What else can I do to help with the electrical infrastructure needs here? So I'm going to share another video that's called Dynamic Load Balancing. While the video is playing, I'm going to explain what DLB is. DLB is, I have multiple chargers, but I want them to feed off of one charger's capabilities. So with the ability to do that, you can see as those cars pull up, without DLB, they were each drawing 22 kilowatts as an example. With DLB set up, I am basically sharing the power from one charger that is hooked up directly to the infrastructure. And as long as the cars pulling up don't max out that electrical infrastructure, they're getting the full 22 kilowatts. But as more cars are pulling up, it's sharing that voltage. And then as cars start to pull away, you'll see that the remaining ones, kilowatts, start to increase again. So I don't necessarily have to have each charger hooked up directly to the electrical infrastructure. I can actually go ahead and share that power. Now that was sharing the power equally. With smart charging, with the Autel chargers, I can control how that power is distributed. I could set up what we call a first come, first serve, which means the first car that pulled up, he's going to get the maximum available, and every other one's going to, have to share what's left. There's several different options, basically. All right, we also have for household usage, so that's more for commercial applications that are going to have multiple chargers. But let's say you have an old house and maybe you only have 100 amp service, but your house has an electric range and air conditioning and it's loaded, electric dryer and all this stuff. So I could either pay and change a service coming to my house, or we have what's called ALM, accessory load management. What this will allow me to do is put a smart meter on my circuit box input, and it will monitor what the max load happens to be set up as. So let's say I set it up as, 60 amps is my max load that I want for my 220 circuits. If it senses that my wife is doing laundry right now in the electric dryer, plus dinner's in the oven, and I plug my electric vehicle into my level 2 charger in the garage, that's going to exceed that amperage load. So it's going to wait to turn on another load. So in that case, since the charger was the last one to be plugged in, until that other stuff is done, and it frees up the actual electricity available. So we have ALM as an example as well. What's on the horizon as far as electric vehicles go? On the horizon, we have something, a lot of talk about going to sodium style batteries. Sodium style batteries offer some advantages and some disadvantages. It's relatively newer type of technology right now. Main difference is we use sodium ions as opposed to lithium ions, and also sodium salts as part of the electrolyte. The advantages are sodium's way more abundant. I wasn't real good in high school, but I remember some teacher told me the earth is made up of 70% water, and a lot of that water is salt water, right? So it's better for low temperature performance, so colder climates, and it's less costly to produce. The disadvantages are it doesn't quite have as long of a life cycle, and the energy density when compared to lithium iron phosphate is not quite as good. So it requires charging more often, right? But that has, as far as technology goes, you know that there's 3 different lithium technologies that I can remember right now. That will probably change those disadvantages as years go by. Another thing that's on the horizon is solid state batteries. So what is a solid state battery? It uses a solid electrolyte instead of a liquid type electrolyte. We'll talk about that here in a second. The advantages are it's a higher density, equals longer range, it's more durable, and allows faster charging time. The disadvantages are cost. It's a newer technology. It's a better, if the worst scenario happens and a fire was to happen, it's worse for that. So what is solid state? Well, picture the electrolyte that's going between the cells was like a solid sponge, kind of like this. So that is what the solid state battery happens to be. It's more durable, right? However, if that were to catch on fire, well, it's not just the liquid and the gases that are basically, sharing this enclosure. I have like a whole saturated sponge, kind of like what we did with that sock before. That whole thing is saturated with it. So it's got a much greater area for the fire to keep burning longer. However, it's better because once a fire's out, it should stay out, right? So that's another newer type of technology. And then we also have smart homes. So on the screen, you could kind of see what we talked about, where we have a solar panel. This is all happening, sooner rather than later. A solar panel, an electric vehicle, a charger, a bidirectional charger, and a bidirectional capable EV. And then we'll go ahead and be able to not only run our house and charge our car, basically off our car and our solar panels, but if I have excess current and voltage available, I can sell that excess back to the utility companies. So that's a huge benefit as well. For those 5 instructors, thank you for spending all this time with me on a Saturday. Hopefully you're finding this, useful for upcoming classes for you. But I did go ahead and give you an example of my go-to EV PIDs. You can just double click on it, not in presentation mode, but it talks about all the different PIDs available to us. And I'll wrap up after I do the last demo here that I have planned for us today, and that is using this scan tool to show you what we have available by going directly to the battery management system as opposed to going to the OBD2 connector. So I'm just going to rework this over here. I got to get some power inside my EV diagnostic box for this to work. I'm going to do the simple hookup real quick. I already did off the camera how to hook up to the 12-volt power supply here of the battery. Actually, it looks like one of them came disconnected. Oh no, it didn't. Good. I'm going to plug this in to my EV diagnostic box. Kind of strategically hold that in place. Turn the scan tool on. I'm going to select high voltage component test. I'm going to select battery test. This is a Kia, as we said earlier. I'm going to say Kia. Here's my little safety warning. I'm going to say, okay, I agree to all that. I'm going to have to read all that, scroll all the way up, say okay. More safety recommendations. I'm going to say okay. It's a USA model. It's a Kia Niro hybrid electric vehicle. Select that from the list, and it's a 2017. If all that looks good, I'm going to say okay. I'm going to let it load its data. It's going to come up with a screen that tells me how to make that hookup. I'm going to say okay. We're going to let it do its thing. You heard contactors closing. I'm going to go battery pack information. And you'll see on the screen as it communicates with the BMS on this vehicle, I have my 4 individual modules. Now each module has several different cells in it, as we talked about. But you can see module 1 and module 2 don't look too bad, right? They're pretty close to being balanced. However, module 3 and module 4 are pretty much dead. I also see an overall temperature here. I can see more here in a little bit. Pack voltage details, depending on how the battery pack was made, there might be more of those little 3 cells across the top in green, and it would tell me the millivolt differences between them. The overall voltage of the battery pack, again, I'm not touching anything high voltage, which is why I don't have my gloves on, but 239 volts, it should be higher because there's 2 modules not working. Overall state of charge is about 57% state of charge, which makes sense because 2 of the 4 modules aren't there, right? What's nice is if I hit the module locations, it tells me if I knew I had to go ahead and service 2 of those modules, it tells me where they are located inside the battery pack. If I go up to the top part over here, battery pack information, it's just going to give me technical specifications about this particular battery pack. It's great for helping determine when you're ordering a new battery pack or whatever. But where it really shines, everybody talks about that first screen with the pretty pictures on it. But here is all the data stream that some of this I could see going through the OBD2 connector, but a lot of it I could not see. So I have all of this extra data available to me that I could never see going through the OBD2 connector before. So with that being said, I'm going to go ahead and put my contact information up on the screen, and I'm going to open it up for questions that people, the 5 of you that have in attendance, I see you guys were typing some of them as we were going. So one of the questions is, how do you cover all of this in your training class, right? So again, I know this instructor, you're an instructor like me where you're going in for a professional technician. So obviously this is not a one-day training class when I do it, right? Because we talked about batteries and I guess chargers, but we didn't get real in depth. We didn't talk about, electric compressors and regenerative braking and motor generators and everything else with an EV. So I have a 3-day class. It's 24 hours in length. That's how I cover it. I usually will spend, the first day covering some safety stuff and everything, but end the first day with the battery stuff. And then the second day we get into motor generators and inverters and converters and all that stuff. Try to do as many hands-on activities as possible. I've got just as many little gadgets made for different parts for the different areas on the vehicle as well. So I got a contactor switching box that the students do with worksheets and all that stuff. I got motor generators that they got worksheets for. So, I create a bunch of different learning environments. So it's a 3-day class to answer that. Another question is, do you sell your curriculum? So sorta. I do have a book that goes along with my training class. So, right now I do sell the book on my website, but I just talked to Carlos Menchu from AES Wave last night. They're going to start carrying the book as well. I also did capture not the full-blown class on video, but a good section of it, which is about a 4-hour-long video broken up into chapters. So I do sell that off my website as well. Where can I find out more information about the Autel tool? So I'm assuming you're talking about the scan tool. You contact your distributor. Your distributor can get you hooked up. Autel does not sell to the end users. So, we go through our distributor network. So we got tons of different distributors. You just want to make sure it's a US-based distributor so you have all the support. If you have a generalized question other than purchasing related question, you can contact any one of us at Autel. We'll be able to gladly answer that, as to maybe who's my closest distributor. We can help you with that. Is the tool capable of doing X, Y, Z or whatever? We can help you with that, that kind of stuff. Where is your next training class? Well, so here's the deal with my training classes. I do training classes all over the place. Some of them are, people will call me up, schools and stuff will call me up and say, can you come out and do a training class? And if we can agree on the prices and stuff, we actually do that. I do some webinars, so I've done quite a few webinars for Autel, and I haven't done one for Electron John yet, but done quite a few webinars for Autel regarding EV. Obviously, I know other subjects besides EV, but I've done those before. Those are free from Autel. Autel has just recently created a whole training center in New York, and we will be doing an EV class, a 2-day EV class out of that training center in New York. You can contact your Autel distributors to get the training cards to attend that. It includes the hotel stay and stuff like that for you guys as well. So that's another way to do it. Also, I do webinars for other organizations. So on the 28th of June of 2023, Mechanic Alliance has partnered with me. We're doing an intro to EV webinar. It's a 2-hour-long webinar. Obviously, it's not going to get real in depth with what we just talked about here today. And looking at the questions, I'm pretty sure I addressed each one, but the 5 of you that actually had the special invites for this, you guys know how to get a hold of me anyway, so you guys can actually contact me direct. So with that being said, anybody else that's watching it, you see my contact information on the screen as well. I want to thank you guys for joining us here today. Hopefully you guys learned some stuff and you found it interesting. I really like gadgets and doing this kind of stuff and understanding how something's supposed to work. Because remember, in order to be able to fix or service anything, you have to have a thorough understanding of how it works. and honestly, the first automotive tool company that comes out with the tools that we talked about. So that other tool that's underneath the scan tool, that's actually a 600 volt power supply. You can use that to power up AC compressors and stuff like that on vehicles. So the first automotive tool company that will come out with these tools that we've talked about here today is going to kind of corner the market and be able to really provide an end-all solution for service techs to be able to not only service batteries on an EV, but also other areas that we didn't talk about today. So again, my name is John, and I thank you guys for watching.